All right, so this is sort of the prelude to the idea of a derivative. So we need to be able to work through this, kind of use this limit, and then eventually we're going to talk about how this connects back to a derivative. So what the difference quotient is this limit. So it's a limit from calculus that we're going to come back and visit later, but I want us to be comfortable with the algebra behind it before we actually get to where it's going to show up in a problem. So it's a limit of some function where we take f of x plus h and we subtract the original function and then divide by h. I'm not going to ask you to memorize this. In fact, if you look at your at your formula sheets that I've given you a couple of times for quizzes, and it's posted on Google Classroom, this is actually on it. I don't expect you to memorize it, but I do expect that you're going to use it enough that it's going to become something that you remember pretty easily. It'll be very familiar, and it's not going to take a lot of effort to remember it. But there's two parts to this. We have the original function, which is f of x, and then we have f of x plus h, which is that function when we replace x with that x plus h. At the very start of this process, we're evaluating a limit. That's the goal. But the problem is I want to evaluate the limit as h approaches 0. I can't plug in 0 for h, right? Because if I do, I get a 0 in the denominator. And that was one of our strategies, was to just do a direct substitution. Just plug in 0 for h, see what we get. This is going to fail, though. So we're going to have to use some of our other strategies that we talked about earlier in the year, such as factoring or multiplying by the conjugate or things like that. And we'll look at a couple of examples that do those things as we work through this. So let's start with a somewhat easy function to begin with. So we're just going to do, I think, 3 examples today. So we're going to use the difference quotient with this function. F of x equals 3x minus 1. Now, my recommendation is you write this difference quotient out every time. That's how you're going to remember it, is if you're writing it out every time. So I'm going to start out this problem by writing out that limit. So I have the limit as h approaches 0 of f of x plus h minus f of x all over h. Now I want you to notice that I'm always putting that f of x that I'm subtracting, this guy right here, I'm always putting that in parentheses. And you'll see why that's helpful as we move through this problem. So I'm going to highlight some things as we work through this together. The original function, f of x, is what we're given right here. So when it comes time to start plugging things in, that's what's going to replace this f of x. The second part of this f of x plus h, requires a little bit more thought and planning. So let's take a look at what that would be. I'm going to work on this off to the side. So if I want to figure out what f of x plus h is, I have to take the original function. And what this means, what that f of x plus h means, it means I'm going to replace my x in the original function with x plus h. So I come back over here to this original function, and instead of x, I'm going to write x plus h. That's the goal. So what that looks like is this. 3, and then we encounter that x. So instead of x, I write x plus h, and then minus 1. Right? So I'm taking the original function, adding in the x plus h, so substituting in the x plus h. It's a replacement. Now, before I go back and start putting stuff into my limit, I'm going to take a minute and simplify this x plus h expression. So I'm going to distribute that 3. I get 3x plus 3h minus 1. I don't have any like terms, so I can't combine anything there. So that's about as good as I can get it. This is what's going to go where that green part is highlighted in the original limit. Man, I've got a frog in my throat this morning. All right, so let's write out what this limit looks like then. So I have the limit as h approaches 0 of some fraction with h as a denominator. So instead of f of x plus h, I replace it with the expression that we just wrote. And that is 3x plus 3h minus 1. Okay, so I took my green and replaced it with green. And then I'm going to put in the original function, so minus the original function, which is 3x minus 1. Notice I put parentheses around that. It's really important that you do that. And I even write the formula so that there's parentheses around f of x. Well, now we've got a limit that, again, my goal is to eventually try to substitute in 0 if I can. But I need to look at maybe combining like terms first. So it's important that as we go through this process, we keep that limit as h approaches 0 in front of our expression the whole way through. So we end up with 3x. If I start to combine like terms, I've got 3x minus 3x. That's 0. So these two things add up to be 0. Then I've got minus 3h. Well, I can't really do anything with that. And then I've got negative 1 minus negative 1. So negative 1 minus negative 1, what is that? Careful. Negative 1 minus negative 1 is the same thing as saying plus 1. So negative 1 plus 1 is 0, right? So these two things should also add up to 0. When you get to this process where you start combining like terms, it should end up with pretty much everything canceling out, with everything being 0. Now, there's going to be a few things that are going to remain, and those few things that remain will all have an h in them. So our expression that we have at this point is this guy, the limit as h approaches 0 of 3h over h. What do you notice about this expression? It is 3. It's a giant 1 of 3, or a giant 1 of h, which means our expression is going to simplify to just be 3. Now, I want to be careful with this. I'm still finding a limit. So it's the limit as h approaches 0 of 3. Okay, so remember what a limit means. It's saying make a guess about what that output will be when you reach whatever our input is, which in this case is 0. In other words, if you think about what 3 is as a function, if I said f of x equals 3 or y equals 3, that is a horizontal line. So if you have a horizontal line of 3, what is the output no matter where you go on that line? It's always 3. So no matter what our input is, it's 3. So even though it says plug in 0 for h, well, I don't have anywhere to plug in 0 for h. So no matter what, this limit is going to end up just being 3. So our final value of that limit is just 3. Okay. That's a linear function. I want to try one that's not linear. So we're going to build a little bit on this. Might use a very similar function here. Let's use f of x equals 3x squared minus 1. So the only thing that changed here is now my x is being squared. So now we went from a linear function to a quadratic. It makes the challenge level of this a little bit higher, but still not bad. Again, I'm going to always start out by rewriting what my limit is. So my limit as h approaches 0 is f of x plus h minus f of x all over h. Okay. So just like the last time, I'm going to take a minute. I'm going to identify my pieces for this expression. So I know that f of x is this, 3x squared minus 1 now. I'm going to have to do a little bit of work to figure out what f of x plus h is, and we'll just do that off to the side. So f of x plus h. All right, so once again, remember, this is a substitution. And just like we did with our induction proofs, whenever I wrote x plus 1 into the other function, I always put parentheses around it. Same thing here. Whenever I write x plus h, I'm going to put parentheses around it. So I end up with this expression. 3 times x plus h squared minus 1. I'm going to take a couple minutes or a minute here and simplify this before I try to put it in my expression, because it does make our life a little bit easier. So you have to remember what the x plus h squared means. Remember, that means that thing times itself. That's what squared means. So I'm going to rewrite it in a way that doesn't allow me to forget about that, because that's important. And then we can multiply that out. So whatever your strategy is for multiplying out a binomial times a binomial, we're going to do that. I'm going to use FOIL. So I'll do my first terms, which is x squared. My outside terms is just x times h. My inside terms, also x times h. And then my last terms would be h squared. And then I have minus 1 tagged on at the end there. Now, before I kind of go to this, before I distribute the 3, I'm going to take a minute and simplify what's inside the parentheses. Just makes my life a little bit easier in the long run. So I have x squared. Now, when you see xh plus xh, when you see this, you have one xh, you add another xh onto that. How many do you have? You have 2 of them, right? So we have plus 2xh plus h squared. And then distribute the 3. So we have 3x squared plus 6xh plus 3h squared minus 1. I want to pause for just a minute, because you're going to see something happen quite often as we go through using this difference quotient, and once we get into the idea of derivatives. This guy, this x plus h squared, shows up a lot. I don't want to have to go through this process every single time. So here's what you can remember. X plus h squared always will end up being this. Right? So if you have an x plus h squared in your expression, if you don't want to go through that process every time, you can go straight to that. It's up to you. You can go through that process to make sure you've got it right. I don't care either way. I just wanted to point that out. All right, so we've got now our green expression. That's this guy. So this is going to go into our difference quotient where I have the green. Let's see if I can keep it on the screen for you guys here in class. Zoom out just a little. That's better. All right, so let's put it all together. So I have the limit as h approaches 0 of something all over h. So I put in the green expression. The green expression is that thing we just wrote. So the 3x squared plus 6h plus 3h squared minus 1. And then we're going to subtract the yellow expression. And the yellow expression is just 3x minus 1. X squared minus 1. Thank you. I was still doing the first problem in my head. Yes, it is still 3x squared minus 1, and that's really important because we're going to find some things that cancel out here. All right, so the next thing I'm going to look for is how do I combine like terms in the numerator. So I have this 3x squared, and I subtract 3x squared. So that's 0. So these two things, when we add them together, give us 0. All right, I guess I could write out what my limit is here. Let me do that. So the limit as h approaches 0, something over h. Okay, so then I have this 6xh that I can write in my expression, plus 3h squared. And then I have -1 minus -1 again. So that's 0 again. The key to this is that you should see your original function, that thing that I've written in yellow, should all pair up with something in the green to become 0. It should always happen that way. That's just how this works. So if it does not happen that way, then you made a mistake somewhere. So a really nice, easy self-check at this point is to say, hey, did I get rid of everything in the original expression? If I did, okay, let's move on. Another thing to look at is what you've written after you combine like terms should all have an H. Every term should have an H in it. If it doesn't, once again, something went wrong, go back and check your work. But I'm still at kind of a place where I'm having an issue because I can't plug 0 in for H because I still get something divided by 0. So one of our strategies that we used earlier in the year when we talked about limits was the idea of factoring. Factoring out a common factor. Well, if I notice that everything has a factor of H, then I'm going to factor that out of the numerator. So in my numerator, I can factor out an H, leaving me with 6x plus 3h. I want to point out, I'm not looking for a greatest common factor. If I were, my greatest common factor would be 3h. That's irrelevant. The 3 doesn't matter. All we care about is trying to find a way to make a giant 1 with the h in the denominator. If we can do that, then we can evaluate this limit. So by creating that giant 1 with the h in the denominator, now I've got it in a form that allows me to evaluate this limit. Because no longer do we have to worry about dividing by 0. Now I can go ahead and do my direct substitution. If you remember when we talked about limits, we said we can do a direct substitution when the function is well-behaved. This is a well-behaved function. If I plug in 0, I don't get something undefined. So let's plug in 0. So when I go to the point where I start plugging in 0, I don't have to continue writing the limit anymore. So we get 6x plus 0, which is just 6x. Now I want you to notice that's a little bit different looking than our first one. Our first limit with the difference quotient ended up just being 3, just a nice value. This is an algebraic expression. This is more common for you to end up with an expression versus a single value. So at this point we've done a linear term or linear function, and we've talked about how to handle a quadratic. Those are both polynomials. What happens when we don't have a polynomial? So maybe we end up with something that looks like this. So this time I'm going to use the function f of x equals, we'll just stick with that 3x minus 1 idea. But this time it's going to be underneath the square root. Okay, so once again, I'm going to start out writing out what my limit should be. And again, I think this is a really important step when you're starting this process and learning this process, that you take the extra 15 seconds to write that out. I also like the idea of highlighting to identify what goes where. So this is now my function, right? So that's going to go where f of x is. I got to figure out what f of x plus h is. So I'm going to take a minute and off to the side, do what we've been doing. Just identify what f of x plus h is. So that means replace your x with x plus h. So instead of x, we'll have x plus h. And then as much simplifying as you can do, I would do here. So maybe distribute that 3, and you'll have 3x plus 3h minus 1. We can't combine like terms. We can't take the square root of this because we don't know what that sum is. So this is the best I can do. This is going to be what I put where my f of x plus h is. Okay. So let's plug all this information into our limit. Let me zoom out just a little bit here. All right. So I've got my limit as h approaches 0 of some fraction with h as a denominator. So that fraction ends up being what we get when we replace f of x plus h with what we've written in green, So the square root of 3x plus 3h minus 1 minus, and I'm going to put it in parentheses, the square root of 3x minus 1. Now here comes the interesting part about the process, right? I can't subtract these. There are two different expressions underneath the square root. You can't combine them. They're not like terms. So I've got to take another approach. And we talked about this way back when we talked about limits, but it's been a while. So we're going to use the idea of a conjugate. So off to the side, I'm going to write a little bit about what a conjugate is here. So a conjugate. A factor, I would like writing it this way. A factor that makes a difference of squares with another factor. Okay, so if I give you a factor and you create another factor that when you put those two together, you get a difference of squares, that's what a conjugate is. So for example, we'll keep it real simple for a minute. X minus 2. If this is my factor, what would the conjugate be? So what if we paired it up with x minus 2, if we pair up another factor with x minus 2, what would that factor have to look like so that the two of them paired up look like a difference of squares? So think about what your difference of squares looks like. What do you think?
Wouldn't it just be x minus 2?
Close.
X plus 2.
Yes. This is the conjugate. All right, so our original factor, x minus 2, the conjugate would be x plus 2. Because when I pair those together, that creates a difference of squares. Now here's what's really nice about difference of squares. When you multiply them out, if we do the whole first outside, inside, last, we get x squared minus 2x plus 2x minus 4. What always happens with those middle terms? So what do you get when you put negative 2x and positive 2x together as a sum?
Cancel?
Yeah, they become 0, right? So these will always add to 0. That's the behavior of a difference of squares. That's what happens when we multiply by the conjugate. And I bring that whole piece of this into the puzzle because that's exactly what we're going to do with our limit right now. We're going to multiply by the conjugate. So if we go back over here to our function, I'm going to rewrite this on the line below because I didn't leave myself enough space. So the limit as h approaches 0 of my function over h. So we have 3x plus 3h minus 1 minus square root of 3x minus 1. Okay, I want to multiply this guy by the conjugate of the numerator. In other words, I'm going to pick something so that when I pair it up with what's in the numerator, I create a difference of squares. So that means I'm going to have this function that takes the two terms just as they are, and instead of putting a minus sign in between them, I put a positive sign in between them. That's my difference of squares. Now I have to be really careful here because if I just multiply the numerator by that, I've now changed the value of that expression. So I have to make sure I multiply by a giant 1. So I'm going to multiply top and bottom of this fraction by that conjugate. So what I'm doing is I'm giving myself a way to create a difference of squares in the numerator. And you're going to see why that's a powerful thing when we start multiplying this out. All right, so we're going to figure out what the numerator is in just a minute. That was the, I can't draw. We'll do this. My fraction lines are not looking super straight today. Haha, I cheated. All right, in the denominator, I don't want to distribute the h. I'm going to start with that. So in the denominator, I'm going to write out what I have without distributing the h. And the reason I start with that is, and I did this in my first period class, and I felt like it kind of messed them up a little bit. It is really easy to forget about this in the denominator and move through your limit not writing that down. And it changes what you end up with. I did it all the way through without it, and then we had to go back and fix it, and they didn't like that. So we're going to try it not that way. The next thing I'm going to do is worry about what happens in the numerator. So in the numerator, I'm going to distribute, but I made this be a difference of squares, which means if I were to do the outside and inside terms and add them together, they have to add up to 0. That's the whole point. So I really only need to focus my attention on what happens when I multiply the first terms together and what happens when I multiply the last terms together. So we'll look at those two things. So when I multiply the first terms together, now you can write this out in steps, you can do this kind of in your head, but I want to talk through what's happening. If I multiply this term by this term, I am multiplying something by itself, right? So that's the same thing as saying, let's square this thing. If I square a square root, what happens? Yeah, it gets rid of the square root symbol. So what we're left with when we multiply the first terms together is just whatever is underneath that square root symbol. Now I think of this in kind of two phases. Then I'm going to multiply a negative something times a positive something. So a negative something times a positive something has a net value of a negative. All right, and then in parentheses, let's think about what's going to be left when we multiply the last terms together. So once again, I'm taking something and multiplying it by itself. And that something that's times itself happens to be a square root. So when I multiply a square root times itself, I'm squaring it, which means I end up with just what's under the square root. Gets rid of the square root. So I have 3x minus 1. Now we're right back in a situation like we were with our first problem. It's just linear stuff in the numerator. So let's combine some like terms here. So if I add 3x minus 3x, I get 0. So those two things added up become 0. Okay, let's write down what we have here. So we have the limit as h approaches 0, some fraction. No! Zooming out all over the place. There we go. That has a denominator of h times the square root of 3x plus 3h minus 1. Plus square root of 3x minus 1. I always start with my denominator because it's really easy to forget to write it, and then you end up with the wrong limit. So in our numerator then, we were able to see that the 3x is canceled out. Then I have that plus 3h that I'm going to have to write, so 3h. And then I have negative 1 minus negative 1. We've already seen how that ends up being 0. Once again, when you get to this point where you start adding like terms together, you should see everything in your original function zero out with something in the f of x plus h part of the function. Now I have this guy. Okay, what do you notice? Yep. So we have a giant 1 right there. That's good. That's what we want to happen. If you don't get a giant 1, that's another place where you can say, ooh, I must have done something wrong. There's no giant 1. I'm in trouble. All right, so we have the limit as h approaches 0 of 3 over, well, now it's just the square root of 3x plus 3h minus 1 plus the square root of 3x minus 1. I don't have that h out in front anymore. So if I want to plug in 0 for h, I'm good. It doesn't create a problem in the denominator anymore. So let's go ahead and do that. It's at this point, once I've gotten rid of that giant 1, that I'm going to plug in 0 for h. So that's going to give us, we don't need to write the limit sign anymore, 3 over the square root of 3x plus 3 times 0 minus 1 plus the square root of 3x minus 1. So 3 times 0, that's just 0. So what we really have here is 3 over the square root of 3x minus 1 plus the square root of 3x minus 1. Now, if you get to this point, that's awesome. If you wanted to stop here and write your answer like this, I have no problem with that. But we could probably make it a little bit nicer. So I have one of these 3x minus square root of 3x minus 1s, and I'm adding to that another one of those. So how many of these guys do I have? I have 2 of them, right? So I can write this as just 3 over 2 times the square root of 3x minus 1. Say that again? No. So it's like saying if you did, I don't know, a good example to come up with there. You have this square root. You can't add what's under the square root. You're just saying I have 2 of these things that can be combined into a single term. Yeah. Yeah. I'm trying to think of a good example that would show why that works, but yeah, it doesn't. Okay, now either one of these is fine. I don't care which one of these answers you write. Now you might be asking yourselves or thinking to yourselves, hey, alarm bells are going off because I've got a square root in the denominator. I don't like that. We've never been allowed to have that before. Here's the thing. Once you get to calculus, that kind of stuff doesn't matter. So leaving the square root in the denominator, no problem. Leave it. All right, questions? So in your Go Formative tonight, you're going to see a couple of linear functions, a couple of quadratics, I think 1 or 2 square roots. And then I've got an interesting one I want you to try that's a constant term, which I'm not going to talk about. We can talk about tomorrow if you have questions. And then there's a challenge. There's a cubic function on there. So if you did one of the ones from the induction proof that had the cubic in it and you were able to work through that, then you should be able to do that one. The very last problem on your homework tonight is a cubic.